Dr. Crouch.
Hello, Jennifer. Math is very important to everyone, but especially to scientists and engineers. We use ratios in every aspect of research in a microgravity environment.
So, Dr. Crouch, what is microgravity?
Microgravity is a condition where the effects of gravity are, or appear to be, very much smaller than they normally are here on Earth. The prefix micro comes from the Greek root mikros, which simply means small. However, in the scientific metric system, micro literally means 1 part in a million, or 1 to 1 million. We use the term microgravity to describe the environment on board a spacecraft in orbit around the Earth. Gravity is everywhere. We usually call it high gravity if it's more than here on Earth, and low gravity if it's less than here on Earth. An example of a low gravity environment would be the Moon. The gravity on the Moon is about 1/6 of that here on Earth.
Hey, 1/6, that's a ratio.
That's right. What are the quantities being compared in this statement? The gravity of the Moon is about 1/6 that on Earth. If you said the Moon's gravity to the Earth's gravity, then you're starting to understand ratios. The ratio 1/6 means that the gravity of the Moon is 6 times smaller than the gravity on Earth. We sometimes use the term microgravity to describe a condition where gravity is not small, but appears to be small. This is a condition experienced on orbiting spacecraft such as the International Space Station, or ISS, the Space Shuttle, and all objects in free fall. That's me appearing to float inside the Space Shuttle. Really, I'm not floating, but falling at the same rate as a shuttle. So to the observer, it looks like I'm floating.
So microgravity is not really zero gravity.
That's right. It diminishes relatively quickly with distance, so it's weaker on the space station than it is on Earth. But it's 6,400 kilometers from the surface to the center of the Earth, which is considered the origin of the Earth's gravity field. Then the ISS is only another 400 kilometers above the surface of the Earth. So at that altitude, the gravitational acceleration is still about 89%, or 89/100ths, of that of the Earth's surface. If the gravitational acceleration on the surface of the Earth is 9.8 meters per second squared, what would the gravitational acceleration be 400 kilometers above the surface of the Earth?
Let's see. You would approximate the gravitational acceleration at 400 kilometers above the Earth's surface by calculating the product of 9.8 and 0.89, or 89/100.
That's correct. By multiplying 9.8 and 0.89, we see that the gravitational acceleration at 400 kilometers above the Earth's surface is about 8.7 meters per second squared. Comparing 9.8 and 8.7 meters per second squared, gravity at the altitude of the ISS is nearly the same as that on Earth. But given the images of floating astronauts, it appears that gravity is reduced by much more than 11%.
So, Dr. Crouch, what is happening here?
Gravity attracts all objects towards the center of the Earth at the same rate. If I release two objects of different weight, and they have room to fall, they will accelerate towards the center of the Earth at the same rate until they meet the resistance in the form of the floor, for instance. In other words, they'll hit the floor at the same time. It's the force of the floor that we feel is our weight. When gravity is the only force acting on an object, then it is said to be in a state called free fall. Objects in free fall can be said to be weightless. Imagine you have an apple on a scale which displays the apple's weight. If you drop the scale, the apple and the scale will fall together, but the apple will no longer compress the scale, so the scale will show zero weight. In the same way, astronauts inside the ISS or the space shuttle are falling around the Earth. Unlike the apple on the scale, both the astronauts and the spacecraft free fall by circling the Earth at approximately 7,870 meters per second, or 17,000 miles per hour. They're falling towards the Earth, they just never get there.
How are the concepts of measurement and graphing important to NASA researchers and scientists?
Research in the space environment gives scientists a new tool for looking at phenomena in ways that is just not possible here on Earth. But these discoveries won't take place without understanding and applying the math concepts of measurement and graphing. To demonstrate how scientists and researchers use these concepts, Dr. Sandra Olson, a microgravity combustion scientist at the NASA Glenn Research Center, will tell us more.
Oh, great. Thank you so much, Dr. Crouch.
Thank you, Jennifer. I enjoyed it.
Now, before we visit Dr. Olson, let's review the math concepts of measurement and graphing. Measurement. It usually tells us the size of something and consists of a number and a unit. For example, the gravitational acceleration at the surface of the Earth is 9.8 meters per second squared. 9.8 is the number, and meters per second squared is the unit. The unit in the measurement is a fixed quantity with a size that is understood. The number in a measurement tells how many units there are in what is being measured. This allows us to compare the size of what's being measured to the size of the unit. For example, Dr. Crouch indicated that the gravitational acceleration 400 kilometers above the Earth's surface is 8.7 meters per second squared units, compared to the gravitational acceleration at the Earth's surface, which is 9.8 meters per second squared units. Notice that the unit of measurement is the same for both numbers. And in case you're wondering, what does the unit meters per second squared mean? Well, 1 meter per second squared, or 1 meter per second, means that for every second of travel, the velocity increases by 1 meter per second. So, if the acceleration due to gravity is 9.8 meters per second squared, then for every second of travel, the velocity increases by 9.8 meters per second. Okay, guys, the next math concept for today's show is graphing. And graphing is really important because it creates a visual representation of relationships that may not be easily determined using numbers alone. And there are many different types of graphs that can be used to visually represent data. There are bar graphs, circle graphs, line graphs, pictographs, and scatter plots, just to name a few. Remember when Dr. Crouch told us that gravity diminishes as we get farther and farther away from the Earth? We can represent this visually with a graph. The x-axis, or horizontal axis, represents distance, and the y-axis, or vertical axis, represents gravity. From the graph, you can see that gravity decreases with increasing distance.